And remember, Karen brings up a good point. She says she thinks her value is really off. We're going to test the class on average. One data point can be wildly off, but that doesn't mean on average we're on average off. So how closely did we measure? 10 inches. Yeah, we got some extra. Yeah, good. Yeah. So we're going to collect some data first. And what I'll do is I'll fire this up. And I don't know the most efficient way of collecting this. No, we don't need that. That's my chicken distribution. Yesterday. Let's see this okay. All right. So, what kind of numbers did we get? We got a perfect 10? Awesome. How many got perfect 10s? We got perfect 10s. We got 1, 2. Just give me the perfect 10s right now. We're going to go around and get everybody's measurements. We got 1, 2, 3, 3. 3 all together. Okay. Give me some other measurements. So we got
9.5.
9.5. How many got 9.5? 9.5. We got 1, 2 of those. What else we got? 9 and an 8. 9.125. How many 9 and an 8 did we get? Just the one? Okay. What else did we get? 9 and 3/8. 9.375. How many of those did we get? Just the one. Maybe somebody else will share a square, Christina. Then you have to raise your hand. What'd you get? 6.5. 6.5. 6.5. Look at that total.
8.5.
8.5. 8.5. We got 2. Just 2?
3.
3. 3 of them thought it was you. Okay, beautiful. All right, what else we got? 9. 9 even. Got any 9s? Got 2 9s? 2 9s. And we'll go back, we'll sort through this data again for you guys so you can get it in your TIs too, so you can play along with it. Go through the motions and actually run the numbers. An extra 6.5 for sure. There we go. Absolutely.
I have to tell you mine. 4.5.
You don't have 4.5?
I have 4.
4.5. How many 4.5s? Just the one? Just the one. And a 4? Did you guys cheat off each other?
No, but I looked over and I was like, well, maybe mine.
Michael!
9.375.
9.375. Let's double that one up there to 2. Thank you, my friend. Who haven't I gotten yet? Ash. 7? 7 down. Everybody 7? 7? No 7s. No 7s.
8 and 11 16.
8 and 11. What the hell's 11 16 says?
It's 6 8 7 5.
There we go. And remember, the TI can do math in its little thing here. So when you said 8 and 11 16ths, I just did 8 plus 11 16ths, and then it kicks it out for it, which is kind of nice. And let's get 8 and 11 16ths. Just got the one. Okay, beautiful. Jamie?
I'm curious, like, when we went to approach how to measure this, before measuring it,
Yes?
what were people thinking? Like, I remember doing it first, like, the 2 finger thing, and then I was like, wait, 8 by 11 piece of paper.
Right, but I said don't measure. Just put down where you think 10 inches is. I was trying to test your innate ability for a distance.
Everybody, though.
There kind of is, but that's a frame of reference versus a measurement. A measurement is basically taking the variation out of an idea. Well, that's what we're going to do. I love when the data set does this, and it always does this. I always get data points like this. What we do is we go in there and we see if we should include them or not, or if they're so egregiously off of the class's average that maybe they're pulling the average one or the other. Who else haven't I got? That's Susie. 10.25. Anybody else do 10.25? Nope. Ken, you had
3/4.
8 and 3/4. 8.75. Anybody else? 8.75? Just the one? Anybody else I didn't get? Me?
11.
Say that again? 11 even. There we go. 11s? James, no. What do you got, my friend?
5
5
3/4.
3/4. Throw one of those in there. Everybody's data now? Everybody's in? Okay. Now, one thing you can do, remember how we used to sort data back in the day in the TI, sort A or sort D? We can sort this too with its frequencies. The trick with this one is you want to keep the frequencies with it. Like, we want to make sure we remember that there were 4 people that said 6.5, but only one that said 4.5. I want to keep the one with the 4.5 and the 4 with the 6. So if you go out to your home screen, and I go stat sort A, if I take L1 comma L2, it'll pull the frequencies with the actual data points. So now when you go back and look, you'll actually have them in numerical order on L1, with the frequencies in L2. So now we can go slowly through it to make sure everybody's got the data. So there's one 4, there's one 4.5, there's one 5.75, 4 6.5, and so forth. So forth. That's the 8 and 11/16. Yes.
Are we supposed to be putting this in our calculator?
If you want to practice running it, I would.
I
mean, that's-
Oh, you went too fast.
How do you
I think we're, like,
Like 10 minutes to collect the data.
well, no, I thought you
We've been
said,
slowly collecting it as we went around. So now I sorted it, and now we're kind of going through one by one.
Oh, I thought you said that we would put it in, and you would put it in and then.
We're going to run it, but I want you guys to play along too. I want you to
I'll
play
just
with.
watch.
No, I don't want you to watch. Watching, I've noticed this. Watching doesn't help you learn. Watching helps you kind of understand, but if you're not pushing the buttons, you don't know what to do when it's your turn to do it. And that's why I want you to get the data in. That's why I sorted it, and I kind of slowly went through it piece by piece to make sure that everybody's got it. Sure. So there's that. Woo! One further mechanism there was.
Been drinking again?
Well, not heavily
Not
today
yet?
yet.
No.
Not yet.
Day's kind of early.
Not quite.
All right, good.
I screwed one up.
Give me time.
how many total did we get?
I don't know. We can sum that up at the end.
I thought it was 15.
Maybe. I don't know. I sum it up at the end. I just want to make sure I got everybody in first before I started summing. Oh, there may be 15 unique measurements,
Yeah.
but with the frequencies it might be closer to 25 because there's multiples on some of them.
Oh,
So,
that's true.
so I'm not sure what. You want to check this down here, Zoe, to make sure your last one is the same as my last one. My last one's at 15. Is your? No. Oh.
It's all
Okay.
good.
Why were you asking that? Out of curiosity.
Because it looks like that we only have 15, I don't know what you call it.
Well, there's
data
15
Right, but there's
data
multiples.
points, but there's multiples of some of them.
I was thinking the same way you were, yeah.
Oh, we can find that out soon.
Okay.
Can you go back up? Because I messed up and I had
Yeah.
to
There you
read it.
go.
Yeah, so Zoe, we're going to find that out soon. And again, you don't have to manually take. Remember how you used to run one of our stats?
Have you got it all?
L1 and L2, and at the end it would kick out an N that would tell you, it's going to do the exact same thing. Yeah, it'll do the exact same thing for you. Oh, as you guys are entering data, something else I just heard from one of your classmates today who went down to the tutoring center to get some help on using the TI, which is a great idea. He was told something I'm a little worried that I heard it from one of the tutors. He was told that if you run the calculate command versus the draw command, you're going to get different results. But the implication was that you're going to get wrong results if you run one or the other. That's not true. You will get different results because when you run the calculate result, you get more than when you run the draw result. And I talked about that in class. When you run the draw command, you get a curve, and you get a test statistic and a p-value. And that's all you get. And that's all you really need. When you run the calculate command, you also get other stuff. You also get the p-hat value for proportions. You also get x bar and s for these guys. You get a sample size in both of them. So it's not that you get anything wrong. You just get superfluous stuff that you don't need for running a hypothesis test. So I'll go chit-chat with the tutors, make sure they know they're not telling people that it's wrong. It's just that it's more than you need for a hypothesis test. So if anybody else heard that, I want to pass that on and make sure that it's not wrong, just different. Not wrong, just like
It's after 10.
Yeah,
I think there's 10, I don't know.
1 and 1.
Scroll down.
Yeah.
Yep, those are our last 2 data points.
Can we go to the top one?
With that,
Can we go to the
Yeah.
top one? Or no, 3.
She will. I wasn't cheating with you.
whoops.
Made
So,
me know today.
what do you think? If we had to make a hypothesis about this data, what would your hypothesis be? What would your hypothesis be? If you had to make a call based on how you guys are ballparking a 10-inch measurement, what do you think?
Most people measure low.
But we're getting low measurements on average. So perhaps for some hypotheses on this one, the claim is that on average we're hitting below the 10 inches we should be hitting. And I'm going to define mu as the average guesstimate, to use a word that is a fun word to say. The average guesstimate of 10 inches in this class. The average guesstimate. It looks like we're guessing a little on the low side, as opposed to the alternative, that we're either guessing 10 or we're guessing over 10. I'm going to put equals 10 because that's usually the lingo of today. There's our hypotheses, friends. There's our hypotheses. Should we test them? I'd like to as well, but I would like to do a couple things first if it's okay with you guys. I want to look at the data. I want to look at it. Why do I want to look at it? Why do I want to look at the data? What am I concerned about here that you didn't have to concern yourself with at all in this exam you just turned in? Why do I have to be concerned about outliers right now?
Use the data.
I'm testing an average, and outliers are going to pull the average towards. And since we had so many kind of very low data points, I'm saying very low in a relative sense. I have no idea. Maybe they're completely within the realm of reason on this data set. But since there were some that were so low and so few that were very high above 10, I'm concerned that maybe those outliers might be artificially pulling the data down. So I want to actually take a look at them and see if they are indeed termed outliers. Let's take a look. Let's take a look. So I'm going to go to my plots, turn 2 of them on, plot 1 and plot 2. I'm going to make a modified box plot on plot 2, because that'll show me my outliers if they are on the left-hand side. L1, L2. Okay. Plot 1 is a histogram with L1, L2. So this is, again, standard fare, the kind of stuff that we're doing all the time at the end of 243. Slapping a histogram and a box plot together and seeing if we get a shape. There is a requirement on the shape of the data. It should be roughly bell-shaped. I say roughly because that's not the hugest deal. The hugest deal really is the outliers, because they really start yarding the average around. Proportions don't care. Michael, you brought up this last time. Proportions don't care because those smallest values are just the smallest values. It doesn't matter how far small they are. But that's why you don't have to worry about testing that kind of thing on the exam you just turned in. When you're testing averages, you really should take a look at those things and say, you know what, I should look at the data and make sure that it's roughly bell-shaped, but more importantly, no egregious outliers. So I'm going to do a zoom 9. Okay, there's my data. Check it out. Check it out. I'm going to change the window a smidge. Just a smidge. The highest guess we had was
11.
11. I want to make it go to 12. I'm going to scale it by ones. This way, I know my smallest guess was 4. The highest guess was 11. If I make the X max up to 12, it gives it the space to have that last bar. So there are our guesses, friends. And check it out. There are no outliers, and this is why I wanted to check. The 4 and the 4.5 are not quantifiably that far down because they're not far away from the next few next to them. It's not like all the guesses were like 9, 10, and 11, and there was a 4 and 4.5. Right. There were 6s in there were 5s in there were 7s in there were 8s in there, and you're seeing that. It's definitely slightly skewed data. And you've got more variability on this side than on that side. But I'm okay. I'm okay running a t-test on this. And you'll see another tool in your project for next week on how to measure normality. In other words, bell-shapedness of a data set. Yeah, Mike?
Based on that far end on the histogram
Uh-huh.
on the right, should there be an outlier there, or is that just is?
Oh, I see what you're saying. Like, so there's this bar that's out here, and there's
Right.
nothing out here.
Right.
The way the TI does histograms, it always assumes data is continuous. So, let me just throw some numbers on here. That's a great question. 4, 5, 6, 7, 8, 9, 10, 11, and 12. This is why I had to change the window to 12. This bar right here is every measurement between 4 and 5, not including 5. Between 5 and 6, not including 6. Between 6 and 7, not including 7. So this one out here is between 11 and 12, not including 12. The highest value we have was 11, which is why the box plot stops right there. There's nothing past 11, but the bar, for whatever reason, the TI doesn't do a very good job of histogramming discrete data like we have here.
Gotcha.
Fair enough?
Fair enough.
Good. Now, I just called this discrete data because I was actually counting the measurements you guys have. But the data itself is actually continuous because you measured it. You rounded it off to the nearest 16, but you measured the data, so that by definition makes it continuous. Fair enough? Good. That's a very good question. Very good question. I think sometimes that's a mystery as to why I always make the X max one more than my highest value. That's why. If I didn't, I wouldn't see that last bar.
Gotcha.
Cool. All right. So let's run it. We've got ourselves some hypotheses. We now need a test statistic, a p-value, and then a conclusion. Step 4. Just like we did on the exam, it appears or does not appear. Does not not up here, that we are underestimating 10 inches. Let's see. Let's run the t-test and find out. So, that tests, and it's right there on t-test. It's right there on t-test. We have data. We have data. We have a null mu value of 10 that we're testing against to see if we're close to it or not. Just make sure you put your data in where your data is, L1 and L2 in this case, in my case. And then make sure you get the sign correct. And once again, here's the sign conundrum that we're in. If you've written your research hypothesis, whatever that sign is, the sign you pulled down here. I mean, you guys can ignore everything else on that line. Just look at your research hypothesis and find that sign. I mean, I think that's, in my opinion, that's the easiest way to do it. That's why I make you write them. That's why I make you write it down. So all you got to do is look at your research and go, oh, okay, it's that one. I mean, you just match them up. Don't worry that there's a mu naught over there and there's a mu over here. Don't concern yourself with that. Just match the sign up. I mean, it'd be nice if the TI had more of an English, or I shouldn't say English, a more stat-centric interface, but it doesn't. It's got a very 1986 basic Pascal interface. But that's okay. Just match the sign to the sign, and we're good to go. Fair enough? Shall we draw or calculate? Your call.
Draw.
Let's draw first, and then we'll calculate second to show you that you're not getting wrong information, just getting more. So let's draw it. We might, let's see, this might, no we don't, okay. Okay, actually I want to pause it real quick before I finish this. If, I'm going to run it again. As it's drawing, I want to ask you a question. If we are indeed underestimating 10 inches, where should the area be? Or where's it going to be shading? Jamie's got to vote for over here. Jamie's got to vote for over here. To the left, to the left, to the left. Has to be, correct? Once again, because we're checking for a left-tailed test. So, what do you think? Are we underestimating? Are we underestimating? For sure. We are almost 5 standard deviations below where we should be if we were actually hitting the 10-inch mark, even within a margin of error, or 2 margins of error, I guess a margin of error, 2 standard errors. Look at your p-value. Here's your test statistic, t because it's a t-distribution. Here's your p-value, 0 because it rounds to 0. So it totally appears that we're missing the mark. It totally appears that we're missing the mark. There's something off. There's something off. We're way, way down here. Now, also, you can kind of tell when you were just simply looking at the graph originally. 10, I hit zoom stat. Let me change the window again. 12, 1. Here's 10, right here. Go so tight. There's 10. You can tell what's going on. If we were hitting 10 on average, the curve would be more that way. It'd be more that way. So we're definitely, and this happens every year. Every year I run this experiment, the same exact data comes up. I get some pretty cool skew. Every once in a while we do get outliers. Somebody goes, I got 2.5. Okay. Totally cool. Why we have rulers, I guess. Why we have tape measures and rulers. But it's great because the data does this. I mean, almost inevitably it does this. It does this. And we miss on average. We miss on average the measurement. Which is, again, why I'm glad we have things like rulers. So you don't have to worry about it, or at least to be able to measure it properly. Cool?
Yep.
Fair-ish? Now, I like these. I like these kinds of tests. But they're a bit superfluous. Or fictitious. They're a bit fictitious. Because this value up here has to have kind of a fictitious value in it itself. I mean, 10 inches itself technically should have a margin of error. I mean, when you look at a ruler, like the one I just gave you, I printed it offline, I checked it against the ones I had in my office, but those rulers have a tolerance. They're not perfect either. They're all based off of some measure buried in some tomb somewhere in Colorado behind hermetically sealed glass, or something like that. There's always a standard of measure kept somewhere, and somehow kept consistent, so that we can base all measures off. You ever think about that? You buy a tape measure at Lowe's, 50-foot long tape measure. How do you know it's actually 50 feet? What if it's not like an extra 1/10 of a foot at the end of that thing? Which you might not care about. But it depends on what you're actually trying to measure with it. It depends on what you're actually trying to measure. If you're trying to put a wall into your house, 1/10 of an inch isn't that big of a deal. You just kind of bend it into place. But if you're trying to design like a nut that fits on a bolt, that 1/10 of an inch is impossibly unacceptable. So you have to have some kind of a consistent measure. So this 10 is a little bit fictitious there. So I like tests where the null hypothesis value isn't more fictitious. So I want to tell you a story about one more test we'll do today. We'll do one more t-test. My department chair, Doug Nelson, years ago, his kids were swimming for Bend High. And back in the day, I don't know if any of you guys swam in high school in Bend. Did anybody swim in high school in Bend? Nobody. So apparently, back in the day, they didn't have the touch pads under the water to stop the clock, so that they take your marks, and they dive. And then the person that wins is the first person to get to the other side of the pool and touch the pad on the wall. Very, very fancy. I mean, I guess it's not that fancy anymore. It's pretty much commonplace now. But 15 years ago, when his kids were swimming for Bend, everybody used stopwatches. So the parents volunteered. Yeah, your parents volunteers down the side. And one very astute parent noticed that some of the parents at the far side of the pool with the stopwatches were using their thumb to start and stop the watches, and some were using their pointer finger to start and stop the watches. And the parent that noticed this had a claim. They said the kids aren't being scored fairly because you're going to have a different reaction time with your thumb than with your finger. That was their claim. Their claim is that if they're sitting there going like this and going like this, the kids, if you check the same kid twice, you're going to get different results based on that. And he brought it to work. He was so upset. He was so upset. And he told me about it years later. And he said, yeah, we never came to a conclusion about this. We never knew how to do it, so the parents just kept doing it. I'm like, well, you can just run a test on that, right? And he's like, what? You can run a test? I said, let me bring it to my classes and I'll have them test it for you. And he was so stoked about that. So I'm going to have you guys test the exact same thing. I'm going to give you some stopwatches. Now, let me turn this off while we distribute the stopwatches.